So good morning and good afternoon, good evening, everyone. Welcome to the AIMEDx webinar today. And so today we are really excited to have Professor Nong Artrith join us for the webinar. So Nong is a tenured assistant professor in material chemistry and catalysis group at Dubai Institute for Nanomaterial Science, Utrecht University. So she was a visiting researcher at Microsoft Research Amsterdam Lab from 2022 to 2023. Nong received her PhD in theoretical chemistry from Ruhr University in Bochum, Germany, for the development of machine learning models for material chemistry. She was awarded a Schulenberg Foundation Fellowship for postdoc research at MIT and subsequently joined UC Berkeley as an associate specialist. In 2019, Nong has been named a SciLog Fellow for Advanced Energy Storage. Prior to joining Utrecht University in 2021, Nong was a research scientist at Columbia University and a PI in the Columbia Center for Computational Electrochemistry. Since 2023, Nong is a member of NL ARC CBBC. It's a chemical building blocks consortium in Europe. So she's the main developer of the open source machine learning package, AIMEDx, for atomistic simulations. From what I know, AIMEDx is the first, or at least one of the earliest open source neural network implementation of machine learning potentials, even before deep learning and the foundation models become a thing. So before we begin, I do want to show one slide to highlight the incoming AI for Materials, Energy, and Chemical Sciences Golden Research Conference. It's a new GRC meeting I'm co-chairing. So we are currently overly subscribed, but you can still scan the QR code to join the waiting list. We are very grateful for the support from our sponsors, including the PPG Industries and Meta, whose contribution really helped us to partially support invited speakers, discussion leaders, and also earlier career scientists. I think without further ado, Nong, the virtual podium is yours.
Yeah, thank you very much for the very kind introductions, Professor Shin. So yeah, hi everybody, thanks for joining the seminar today. So as my title that I'm trying to show you from my own experience, actually I myself, I'm a computational material scientist. I really started doing the modelings from atoms from first principle calculations like DFT. But I always try to, I have a dream that how can we really make use of computational for like a material discovery. And in this case, I want to really look at like the catalysis discovery. That's why, yeah, the path of my journey of academics and also like a scientist, I'm lucky that I can really enter to the machine learning field, and I want to show how machine learning really can help as a pathway for catalysis and also material discovery. So this is the overall of my research group, the activity that we are working, as I already mentioned, that our team, that my own expertise, we really developed quite large DFT database on any kind of like material that related to the energy materials. But we can always do large DFT database, but most of the time our work is very valid or really reliable or really is make sure that it's really work. We always collaborate with experimentalists to either validate our predictions or really hopefully that what we predict is really work. That's why the group is also collaborate with experimentalists that can also generate experimental data. We also making use of machine learning for predicting material properties and also data mining that also lead to the material discovery. The material that we are looking at, like energy storage, like battery materials or energy conversions that I will discuss today. And most of the time that machine learning model that exists in the public or open source, most of them are okay and work for our own applications. But if sometimes it doesn't work, we also develop our own machine learning models. Like Professor Shin mentioned, we develop atomistic energy network, which it really can use to generate machine learning model and also apply for the application. This is the overview of my research activities. But still, I have been working on the field for so long already, but it's still not yet there. What is really holding back computational material discovery or catalyst discovery? Because of this day, right, many of us making use of the AI chatbot. Most of the time that it is you get the answer more or less that is quite okay or reasonable. But when they start to ask the question related to my research, a question that I have in my research group, it never get the answers. So what is this there? I think this is we are not yet, but I hope that one day it will work more or less. That's why I have to come back to the point that where we really considered, because of there are so many factors that is still holding back computational catalyst discovery. The key 3 points that I would like to discuss today, actually there are many factors, but I believe that these 3 focus that could be idea why we need to do that. For example, the simulation tools that we use, for example, the DFT, how accurate it is to describe material properties that we would like to describe what we really would like to have. I think in this day is accurate enough to discuss the properties. And the second part is it like, do we have enough and reliable data that we need to learn catalytic behavior? And another part is it like the model that we simulate, is it realistic enough? Is it really account the real world and also non-idealistic in our models? So these 3 points that I think this is important. The first part, I think that model that we have, like DFT, is quite reliable. As you can see that there are a lot of DFT opened and shared public database, for example, material projects, and also many others that I cannot even name all of them. And this is the database that my research team making use. We can really generate a lot of synthetic data that really can do that. So what is it really the way that we looking at the catalyst discovery, right? In this case, I'm making use of one example, like how to look at the lithium-ion battery electrodes. We always make like the material concept, and then we do a material synthesis, construct the division, and test the performance if it's good or not good. If you are lucky, if it is great, then you are done. Then you can really do the next step. But most of the time, when we start to do that, starting from the concept until to looking at the performance, it's not always work. That's why for computational modeling, we can explore, hopefully can explore large and more chemical space. So in the past, we have the target like the red compound that we have is here, the red color code. We might do high throughput screening in a way like a random. When we have this, we always have to think when what we see and then put it in libraries, and then we can use some tool for data analysis. And then we predict the properties. If this is good or not, we go to the experimentalist and ask, please validate what we predict. You see, when we don't screen to the right target, we also got nothing out. But from the time that we have much better, we have more computational resources, we can do high throughput virtual screening, and we get a lot of data, which is also nice, but then also spend a lot of resources. But at the end, we have to really go to our experimental colleagues and also test how material that we predict from computational is it working or not. And this day, we have really smart way automate virtual screening, making use of like a genetic algorithm or generative models to generate large data, and then with the tools, and then sort out and filter what could be a good candidates. But at the end of the way that we do computational screening, we always need our experimental colleagues to validate and to make it sure that it's really working. So what is there? I think the limitations of the current synthetics or computational data, I would say that synthetic is fine, but experimental data that can be we need it to do that. And I believe that it's lack of like a homogeneous or standard and also the reliable experimental data that we really would like to see. Is it also not that easy? But as you can see that in the recent years that the automate lab generate a high throughput experimental data, this is coming. So I also lucky that I did a postdoc in the SEDA group during that time. They also finally show the automate lab that is coming. This example, this is shown in the solid state battery that looking at. Is it really fantastic that now this is a combination of the computational database and now can also use machine learning model and suggested what could be the good candidate, and we narrow down and can do automate lab synthesis that you can have. So I think in the sooner or later future that we will have really a nice data, both computational data and also experimental data. This is really nice in the future. So, but again, my own lab, I don't have automate lab. But what we can do, I think from computational side, that we could really making kind of like a very exciting to contribute to the field. But what I think I would like to discuss is how the model that we use to put in the database, like a computational database, is it realistic or not? So my contributions in the community, I think our approach that making use of highly accurate and efficient machine learning into atomic potentials can help to scale up the accurate DFT to complex and also realistic structures that include in the database. We also know that the DFT data that we have is in the past, we use like a quite efficient GGA, like on the left-hand side, this is a PBE plus U. So we still have the comparison between experimental formation entropies, this is per oxygen molecules on the x-axis. On the y-axis is calculated from the DFT, this is the GGA plus U. So there is some kind of like the scaling that you have to add on the time to make it accurate. But already many scientists that making use and test, including my own self, that using the method GGA is already improved this missing. So I think for energies, it's already kind of like using method GGA, like R2 scan to describe tangent metals oxide. It's really quite okay. And this is also the class of material that we making use for a catalyst. So I hope that, I mean, there are so many different group doing such a research, make the DFT is more efficient and also more accurate. And now the next thing now, how can we really combine everything and all paths for catalyst discovery? So I have to say thanks to the pioneer that they really have already built up the way that we can really hopefully that can make decision and also identify what are good or not good catalysts. By, for example, we learning from the binding energies and also reaction rate. Like on the left-hand side here, this is the volcano plot. So we identify the catalyst that making like a not too weak and not too strong by the energy, and then we identify this could be a good catalyst. Or another part that we also learned that a descriptor-based physics in the intuition-based descriptor, looking at like a D-band centers or the scaling factor could also be a good. But still, we cannot find what is it really could be a directly like a good descriptor, and then we can make the decision. This is the great catalyst for any reaction mechanism. So we think that if we have machine learned descriptor, could be the direction to go. I'm not sure, but recent at the moment, there are so many research groups very active in the fields. We have the question that can really machine learning identify models and what is really the previous model is missed, and can we really use machine learned descriptor to be one of the way that we can test. So what we would like to test, we making use of one reaction example. It is just a showcase. It's not for general for catalyst discovery, but we pick one reaction to demonstrate. For example, by bioethanol reforming, which is very attractive for hydrogen productions. Ethanol reforming, this is the key step, right? Like you can see here, this is very nice, simple reaction that we can see. This is ethanol that we can get like a CO plus carbon and also get the hydrogen. And this is what we think could be a good reaction that we would like to try. And however, the side reactions sometimes make ethanol reforming is inefficient. of course, the platinum catalyst it also shows some kind of like a competing reactions that happen there to the reforming of the ethanols. For example, here on the reactions on the second equation that I'll write down here, sometimes it's loss of hydrogens to the CH4. This is also have less hydrogen. Also, sometimes the catalyst also like deactivate. So how to do that? So if you would like to find a new catalyst to replace or to change from platinum, we have to really looking at more catalysts that is it have more selective ethanol reforming. And what we have to do as a computational catalyst doing, we have to find experimental data that we can find to validate. So we found that together with Professor Jingwang Chen from Columbia University, they did some experiments already for two kind of like a platinum-based monolayer bimetallic catalyst that can be active and also selective for ethanol reforming. On the left-hand side, this is a model, the platinum as the core and the 3D transmetal as the shell. And another model on the right-hand side here, the platinum as a shell, and then mix some like a more cheaper or more earth-abundant transmetal. So we have this model, and in experiments, we found that there are a few candidates that already show and reported experimental data. And then the questions for the modeling or the theories, are there others transmetal is better? So what we start to screen, of course, like activation energies to really looking at important. In this slides, I will show some partial reaction network that we can looking at what is it the rate determining steps that likely be the key. For example, bond breaking up the carbon-carbon or CO bonds to looking at there. So this is the reaction that we consider. This is the ethanol, and the orange color, this is the CO bond breaking. The blue is the CC bond breaking. And there are so many different reactions and also many different parts that we can really get into what we want to have. And if you would like to change many different catalysts, we have to consider all of this. So what to do that? Doing all of the FT calculations, it will be very time consuming. We think that can we combine the DFT and also machine learning to help to identify the activation energies. So what machine learning needs is that the number. So we decided to put the number at each reaction so that we remember that. So we have in total 14 reactions that we would like to consider here. For example, here I named this CC bond breaking. This is 1, 2, 3, and so on until 14 reactions. The blue is carbon bond breaking. The orange is CO bond breaking. So let's see, this is just a number. And then we very many different kind of the catalysts that we consider. So I hope that we can train machine learning model to predict the activity and the selectivities of those two models that I showed before. So note that we have only 7 experimental data, but we can really generate a lot of DFT data to include in our DFT large database. And how can we combine these two types of data? So we think that we can making use of the two-step approach. We first start to analyze and also to collect the large DFT database, and then we identify the targets that we would like to predict, for example, tangent state energies or activation energy to identify. And then we extract and try to learn from large DFT data that we can predict activation energies, and then we learn, and then we will make use of or extract the knowledge that we can gain from second machine learning models. Is it connect to experimental data to predict the activity and selectivities of the ethanol reforming. So I will briefly show the models, how we do the two-step approach in the next slides here. So the two-step approach that we have, the first model, we're making use of nonlinear to predict the complex DFT data, which we get it from, for example, one method that we use not elastic band to estimate activation energies. And the descriptor that we use it to put in the model, for example, binding energy, reaction energy, chemical species, and so on. There are many different descriptors that we have. I also share what we have done here in the open GitHub repository if you are interested in. And then we predict the tangent state and activation energy. And then the second models, we also learn and predict and we get. We combine and connect. We identify the descriptors. Again, visit binding energy, reaction energy, tangent state, and also activation energy that we get from the first model to looking at the targets that we would like to predict the total activation energy, the reforming activity, and reforming selectivities, but connected to the experimental data. So let's have a look at the first models. First, we are making use of machine learning to accelerate it to estimate the tangent state. This is the not elastic band. You can see this is one example to showcase like a CC bond breaking that we have. There are the gray, this is like at the top, the monolayer, and the purple, I mean the color code, the blue and green, is it to represent earth abundant material that we could use as a core, so that you can do screening of many types of the catalysts there. And we're making use of Gaussian process regressions to really estimate the activation energies. This is really like the GPR model. Is it refined with the Bayesian sampling until we really get the uncertainty that for all energy are very small. And this is very efficient methods. The method is developed by Jose and also Professor Brigard. At that time was in Stanford and now moved at in the DTU. So we're making use of this GPR model, and we really can get really very efficient and many activation energies in our database. So let's have a look at our first model that we use, the nonlinear model, to looking at tangent state energies predictions. The feature is on the left-hand side, and on the right-hand side, this is the prediction that we have. So this is the DFT tangent state that we have. The model that I have is it here. We screen and we get a lot of data, but not all of the data point that I could put and show in the graph. But overall, that you can see that our predictions, that the combination that we used, it, the machine learning model that we combine another GPR plus random forest to really find how our DFT tangent state close to DFT. So we use of the live-one outcross validation score to test that. We found that it's really very excellent. It's good agreement with the DFT. You can see that it's around zero. The CV score is around 0.31, and also mean absolute error also very small, like a 0.20, which is really very nice. Another model, this is predicting of the experimental reforming, because we have very small experimental data, only 7 data points. So we use the simple linear models. The data that we have, remember that we have 14 reaction energies, and the tangent state that we get is it also the 14 tangent state energy that combine also between DFT and machine learnings. So based on that, that the predictions, we use the lasso model to identify the important reactions. And we found that the reforming activity models based on these 4 parameters, like you can see here. So the number here is it really based on the index that I list before in the 14 reactions. And it's really key important part that you can see that for the reforming activities based on these 2 reaction 1 and reaction 2, this is identified for the key important for the CC bond breaking, and the reaction 2 is the CO bond breaking, which is really nice for us. And what about the next one? Reforming selectivities. So the selectivity is must lie between the 0 to 100% or 0 to 1. So we fit with the logit of the experimental selectivities with S, and we use this simple logit that we fit, and this is the number that we have for the coefficient of the beta. We also vary, and we find that the rescaling is equal to 10, it works best. And the result that we got from the lasso models, and we and also the logit selectivity model is based on these 5 parameters, and this is what we get. And this is what we have. And we found that the reforming selectivity, it depends on these 3 reactions. So reaction 1 is also the same like activity model. And now we get more, this is reaction 3 and also reaction 4. So I list it down here so that you can remember. So these 2, 1 and 3 is important. This is CC bond breaking, and number 4, this is CO bond breaking. This is happen for reforming selectivities. Now let's have a look at the predictions. So we start to validate of both on the left-hand side, the activities, on the right-hand side, this is selectivity models. So on the x-axis, this is the experimental reforming that we get from experiment, and this is the predictions that we have from the y-axis here. So as you can see that both on the left and on the right, our machine learning model predict is really super accurate and really very nice. We are very happy about the result that we get is there. And then we think like our model is so good. Is it very nice? Let's have a look and analyze a little bit. So we know that this is the best known that they are a really good catalyst for this model that we have, good for the reforming activities and also reforming selectivity, the best known. But what model that I have, that I put it in the also a really excellent reforming activities prediction and also excellent reforming selective is cobalt, platinum, platinum. But we didn't see in any reported or in any literature. I think this is maybe because of one is missing descriptor that in my database is that we didn't include the key important part is it the stabilities of the catalyst, which is also very difficult and also hard to predict, and also we need to confirm with experimental confirmation. So with that, I think this model is quite accurate and also see, and also for validation, I think the model really list is there. Then we also still have the question next, like, can this model really predict beyond the alloys that we trained it? So I generated more database that is it not the similar to the model that we have, like only alloys. We're looking at also more earth abundance, for example, molybdenum nitride or molybdenum carbide and many others. And then we found that based on the model that we have, I found that the platinum coat and also the core with molybdenum nitride could also work best as a reforming activities and the same time reforming selectivities. And then I discussed with Professor Chen's group at Columbia, would it really work? And then they test and try. And yes, the experimental validation and confirm that the model that we predict could also be a great alternative, or the great catalyst that could be good for ethanol reforming, that give the best performance for reforming activity and also selectivity. We are very happy with this simple model. So this workflow is done and also can also predict really nice. For the first part that I would like to give as a take-home message is that even for very simple model that we demonstrate here, already show that our machine learning models can also create the model and also can transform to slightly different class of the catalyst. It worked okay. But of course, this is not general, but I think we are very happy with our showcase in this way. So if you are interested in, this is the tool and also some database that I showed that you can really making use of our model. The next one that I also would like to discuss in this seminar, I think that doing the complete reaction mechanism with computational catalysis from atomic simulation, doing the whole reaction mechanism is really complex. For example, you have the CO2 and you would like to looking at CO2 reaction, right, to get the methane and oxygen. The catalyst, like the nanoparticles, until you really get the molecules to the surface, go to reaction intermediate, until you get to the product. There are so many steps involved, like you can see here. And can we really making use of machine learning model to simulate and to follow all reaction mechanism like this? And this is the target, and this is the idea that I would like to discuss in the next chapter of my talk. So our group also making use of a machine learning model to learn from highly accurate methods like a DFT. Like in this diagram, the x-axis, this is the, let's say the model or the atomic size that you can do simulations. On the y-axis, this is the approximation of the accuracies. If you want to really describe the property highly accurate, we're making use of DFT to describe the accurate electronics property. And in realistics for complex molecules or complex interface heterostructures, including sampling that we can understand the complex realistic structures. We use a machine learning model to learn the relationship between structure and energies, and put together with sampling methods like a molecular dynamic simulation or Monte Carlo simulation to follow and to looking at the reaction mechanisms. Also, the simulation scale can do really from like thousands of atoms or even like 1,000,000 of atoms. So this is what we will discuss to apply to our catalyst. Because once we have already really highly accurate and efficient machine learning models, I hope that we can really describe bond breaking and forming bonds that can describe reaction mechanism and includes more realistics like a gas phase, liquid, solid, and also the complex interface. And hopefully we can also identify non-ideal structures with some defects or include some solvent effect and also like electric fields for electrodes catalyst, for example, which is not yet there for realistics for the first principle calculation. This is what our group developed the model that can, hopefully it can really describe how the methods work. So we use the models to learn from electronic structure theory and learn how atom interacts. We really create, again, large, reliable and accurate DFT database, and we're making use of machine learning models to train and interpolate the relationship between structures and energies, and also get the forces and also many other properties. We construct highly really accurate and efficient, continuous, efficient machine learning potentials and use it in sampling methods. This is implemented in our AIMEDx. There are so many different machine learning models, but our group use artificial neural network because it's really highly flexible and also can reproduce the reference methods really, really accurate. There are so many different methods, but the bottleneck, like you can see that making use of neural network models to understand and to find relationship with the structure and energies, neural network need large data to train and to get to the target. For example, if the target in this show simple case is it a hydrogen bond or distance or the dimer on the left, on the x-axis is it the distance, and we would like to reproduce the linear zone energy. The target is in gray. The DFT data points, we need to have enough data points to describe correctly the linear zone as original sample. So of course, we as a beginner, we don't know how large and how big data that we need to generate until we really get machine learning potential to describe complex potential energy surface to describe our application. So what we demonstrate is that we have a few steps of the workflow, like I already just showed before. We have the data, we do data analysis, we select the models, we start to test the application directly so that we see where it's failed. Most of the time at the first initial data set, it's not really working. We do iterative refinements and including the active learning so that we do this until we get it to our application accurate. The active learning that we did, we directly jump into your sampling methods. For example, you construct machine learning potential, and then you do MD simulations, and then you compare if the error that you have from your prediction is it very large from the reference data. If it's really large, like you can see here for the training set 1. In this case, we decided to compare what is it really large. We include them in the training set and do this iterative refinement until you get to the accuracy that you want for your own applications. This is for your references, our atomic energy network. If you are interested in, I would be happy to also discuss or to help you to get started, but not discuss this today, just for your references. Let's have a look at how we apply and use our models to complex energies. We have done a few examples, but today I plan to discuss only one example to show you I mean, 1 or 2 example if I have a time to looking at the complex copper gold alloys for CO2 reductions. Because we know that copper is an excellent and good catalyst, but it's not really stay in the reactor. It's too long, like you can see here from the experiment. This copper alone is really oxidized and also not stay in the reactors very long. But once we have another element is this gold, it really make the reactions last longer. This means this mix copper gold, it really make the catalyst stables in aqueous solutions. But for modeling for such a large nanoparticle, 5 to 10 nanoparticles, it's really difficult to describe with first principle calculation. We construct a machine learning model and try to reproduce and to understand such a large nanoparticle like this. So we use machine learning models to help to identify the relevant composition and also surface structures in the aqueous solutions. So we construct the first model with the in vacuum. We're looking at many different cluster sites. The orange is this gold, and the orange is it copper, and the yellow is this gold. We combine machine learning models with Monte Carlo annealings to find and to search where the copper and gold atoms sit. We can see that in vacuum, the copper like to rearrange inside, and the gold stay on the shell like a very stable on outside in vacuum here, which is really show that the gold like will be more stable in vacuum here. And we compare this the time that we're looking at with DFT with around 200 atoms. We use a CPU time like a 16 cores is around 3 hours, but with our machine learning model it's around 1 second. And with 4,000 atoms, it's around a cluster size that we would like to simulate. With DFT, it's very a challenge, but with neural network, it's around 1 minute we can do such a simulation already, which is very efficient. And then once we have really efficient and accurate model, we can sampling whole of the phase diagram and many different compositions, and also see we can looking at if the structure is really stable, the combination of grand canonical and this simulation. So we found that with like a 1000 Kelvin, the copper cluster is start to melt, and this is really nicely to show. So this show already that we have quite stable and good machine learning models. And not only that, we can also extend our data to more complex with solutions. As you can see now that when we do a simulation, when we have the copper gold and also with the solution, the rearranging of the copper gold is also slightly different from in the vacuum, because you can see now the copper also like to come and to do reaction with the solution. So this is really important that you do realistic simulations. But however, to get such a model to do your simulation, we really use really large and big data. In this case that I spend time and I do the DFT calculation around 50K DFT data points until we get, which is really large. Yeah, for the beginner or for like a new student would like to start until there, it would take really a lot of time. That's why I think the model that we do, I think it already can capture the realistics and looking at larger scales, and can also looking at more complex structures. But then the question that we have still like how large of the data we need to get until we do such a complex simulations. That's why we try many different ways to do that. The first thing that we think like in practice, because we know that to construct machine learning potential that we do is that we need a lot of data until we really get is that we have to think about the database, right? It should be large until we get a correct potential energy surface, but then the sampling also very important, and training maybe also very expensive, and what to do and how to do that. We think that we know that based on our communities and also literature that using the GPR basically it's kind of like a very nice. It works very well and really accurate compared with neural network models, which is with GPR, we can use small data set. It can really describe the target. It's quite accurate. But with machine learning model, we need a lot of data. For example, here you can see that this is done with our postdoc in one. Even neural network cannot capture the minimum distance accurately. And also the training cost for GPR, it take a bit large or more with the kernel base. And for neural network, it's quite efficient. And for the transferability of large scale, I think it's quite not very great. In neural network, it's quite good there. So how about this? If we really try to combine both methods like a GPR and ANN, maybe it is the best way to do that. For example, we have the reference data set for these complex molecules, and then we start to looking at by use the GPR to have like the less DFT data points and interpolate and looking at uncertainty database and refine that we can generate synthetic data, and then we use it and then we get the synthetic data. We don't need to do DFT data for the prediction that they get the new data from the GPR model. And then we can really combine and we get the database that we can get the GPR, and then we train with neural networks, and then we get is quite accurate. This is the in one demonstrate as a benchmark with the heterogeneous database for lithium ethylene carbonate, many and variety of the structure and the data that we have. So for example, some MD samplings of the lithium is it in green and ethylene carbonate is it on the small molecule here. And we get some kind of like also random displacements and also the clusters and also internal sampling and get such structures. And in this example that we have, we train the data with highly accurate with the HHA06 with hybrid functionals. And in total, we have around like 5,000 DFT data, some part to use it to train machine learning models and some part to use it to test our models. Let's have a look at the accuracy that we train. First, if we train the data without any, including the forces in the training set, this is the forces error. You can see that it's quite large errors, but making use of our GPR model that we use together, this is generate the synthetic database with the neural network. So you can see that quite good accuracies. Only some data point is outlier, but is it not much. But we use the direct force training. So a lot of data points is it outlier. It's also depending on the method that you use to generate the forces from the DFT. So our model predicted the forces also not that great. But then the way that you use to training the forces to get is, if you use directly the direct force training, we should really use a lot of RAMs, and we use our model, the combination of the GPR that generated the synthetic database with neural network, really use load the RAM, and easily make it very efficient. And so hopefully that the combination of our method, that GPR and ANN, that solve the problem that we get large data. And this is the first thing that we try to do. And how about the second one? So we also thinking that like we know that sampling method is also very important. Most of the time that you sampling the MD simulations, you might end up with only local minima. And doing the NEB is also nicely spread, but most of the time that how large of the distance or the way that you would looking at the images. So we're thinking that like the combination of both maybe generated data from the MD simulation and also NEB could be a nice way to do that. And in one, demonstrate with the copper atom, the gold atoms on the surface of aluminum. And then we see that if you really sample the data from NEB and also get this NEB on the red dots, black dot here, and also get the data from MD simulation. So this could also be a nice way to really sampling, and hopefully in this efficient method to generate data could also help you to generate full potential energy surface. Yeah, and then we start to compare and start to look at such MD simulations. On the on the right hand side is to show how you run a quick MD simulation, and then to test and to see. And we train our end with the MD and NEB. It's a really nice way. So basically, just to having a quick test to check if you generate the database, is it efficient enough to capture the potential energy surface. So those methods is really helped by testing if we can run the stable MD simulation. So the answer is yes. Yeah. And yeah, and we already implemented. And if you are interested in, we also publish the workflow that you can making use of ANET GPR to generate database, which will really help you to get the data, and hopefully it make your machine learning model stable that you can use it for your own applications. All right, so this is just a recap. But now the next thing that we could also making use of already publish the machine learning models or the data that we have. For example, we can do transfer learning, because of, as you can see now, there are so many foundation models or universal machine learning model that you can use. So in this case that we demonstrate that you can use the model that already appeared, we making use of, in this case, the open Catalysis database 2020, and then we train or pre-train, and then we transfer the knowledge by do fine tuning, and then we fix some part of the model that we have, and then we retrained with the model that we would like to do our applications. We demonstrate to our own, the previous one with the couple goal, that we use it like a 50K DFT data points, but we use the transfer learnings idea to work with such a big open Catalysis project database. We do the simulation more or less the same, like the data that we wanted to do with the stable MD simulation. In this case, we use around 1000 DFT data points. It's already show that we can get quite a stable machine learning potential to describe the complex copper-gold water. And another way that making use of foundation model or use machine learning potentials as a framework, hopefully that we making use of those type of reliable or at the starting point, but to apply to our own applications, we have to do fine tuning. So we met Professor Gaposhanis, and then he showed like a maze model is quite good as a starting point. So there are so many different machine learning model that you can start to use, but we pick the maze models. The reason that we pick the maze model because it's also have a good complex interface structure already. We demonstrated of making use of the foundation model to understand the complex reaction mechanism of water splitting, especially the dope of the earth abundance catalysts like a barium titanate. In this work, we looking at how we would like to go to the reaction mechanism that describe hydrogen electrolysis or water splittings. This is the simple chemical reactions in electrolysis. On the left-hand side, this is the cathode side or the HER. On the right-hand side, is it the anode or the OER. So we think that on the right-hand side, this is the OER is quite complex, and we would like to focus and looking at this in this showcase. The reason is that oxygen OER here, we know that the catalyst that could be a good is it like a metals oxides, and you can see on the right hand side the benchmark of the OER electrocatalyst is really compared with the on the y-axis. This is all potentials. Iridium oxide have really the good ones, and many other like more earth abundance could be a good candidates, and we would like to try to understand why this is good, and can we really replace or even find a new type of elements can use, and hopefully reduce the over potentials. Basically, we focus on these reactions. For example, here, this is the 4 reactions tangent state that we would like to focus. This is the, you have the first, this is like the catalyst that we have, and then we get for the first one, this is like OH. minus, and then we get like a OH as the intermediates, and then get oxygens on the surface, and also until we get the products like the oxygen molecules. So the reason that we're looking at the barium titanate because it is like earth abundant, like you can see. And based on what we are trying, we always look for something for validate. And before we start to construct our machine learning models, we look in literatures. If there are or there were literature experimentally reported. And we are lucky that at the time we found a few experimental reactions that describe that we can really follow. So we making use of these 3 papers to really describe some reaction mechanism that we can use it to validate and to understand our reaction mechanisms. In 2016, I already start to looking at dope, and we pick 2 elements like iron dope and nickel dope, and we found that it could be a good potential that iron dope barium titanate and also nickel dope barium titanate could reduce our potentials, and then we start from that. But in this work, it is only DFT, and we would like to, of course, follow the full reaction mechanism and also including samplings like MD simulation, but it simply is very expensive. If we also include more realistic, like more water, it will be very large. That's why machine learning models that we would like to develop and construct could be a way that we would like to try. This is the main foundation model published at that time. It's in 2023. It is consists of like a big and large data of the bowl and also some surfaces here that you can see. The model trained on the GGA plus U database, which is also good to generate and also to get the structures. So we start with a maze model, and we found that 100% that we did with maze model or MD simulations or sampling and get the structure is really stable. But when we start to do fine tuning with a maze model, it's quite challenging because of the training is really it's not very efficient. Since we already have our own workflow with our ANET, so we decided to use maze model to quickly generate the database. And then we refine or fine tune with our machine learning model with our ANET. And then we take these opportunities to improve the accuracy of the DFT. We use the DFT functional with the RPBE and include van der Waals corrections and also include the spin that hopefully it can be more accurate to describe our reaction mechanism. And this is just to have the benchmark to compare why we decided not to use the final maze model as a fine tuning, but we do fine tuning with our ANET models, because the ANET model can make it quite efficient and also give accurate machine learning potentials. This is the overall of the database and also model validation that we have. We get a lot of data that based on variety or diverse of the surface structures and also the molecules that could happen during the reaction mechanism. With the maze model, we have around 10K DFT data points that already help you to looking at the reactions quite okay, but not yet there. We do a few iterative refinement with active learning, and overall at the end, we have like a 16K DFT data points included in this training set and can describe the full reaction mechanism. This is model validations to looking at the structure. Of course, we would like to describe bond breaking and formings of the water splitting. It's a really highly accurate machine learning model to describe radial distribution functions of OH and OO and HH that's as accurate as the DFT. Also another, we also observe for sampling of MD simulation, and then we compare with the DFT, which is we are very happy with our model. This is demonstrate. And then we use our machine learning model with the sampling method. This is the metadynamics to describe the reaction mechanism that we would like to describe, like I just showed it before, from tangent state 1, 2, and 3. With this, we really can follow the full reaction mechanism that we would like to describe. On the left-hand side of the movie that we have, for the first reaction, tungsten state water dissociation. On the left-hand side, that is only bare barium titanate. We use oxygen as observed. Actually, oxygen is in red, but blue is the oxygen atom that we observe. On the right-hand side, this is a nickel dope. The reactions on both on the left and on the right occur the same, but the reactions with nickel dope have a lower activation energy or the barrier. So the second one, this is the oxygen formations. So you can see that the reaction really can follow the full reaction mechanism with our stable machine learning potential that we generated. We are very happy about that. We generate our machine learning model with many, because they have really low RMSE, and we don't know what to pick. And then we pick all of the machine learning models, and we run the simulation more or less actually the same. And is it very happy that the simulation is reproducible, and we really can confident that our model is accurate and can run the simulations and the full reaction mechanism. Yeah, this is for the first time, even for my own self, that during my research time, this is for the first time that we can really combine machine learning potential and looking at the full reaction mechanism until we get like oxygen molecules. If you are interested in, this is the preprint for more details. Just looking at summarize what we have seen, what you just saw in the movie there. So this is the x-axis is the collective variable, the oxygen on the surface and the hydrogen that you can see. On the left-hand side, this is the barium titanate pair, and on the right-hand side, this is the nickel dope that you can see here. And we follow the tungsten state 1, 2, and 3 until we get the product as oxygen molecules. This is really very nice and to show. And as I already mentioned, that the free energy or energy profile, we don't do just one MD simulation. We run 10 MD simulation, and I would say more than half, it really give the same reaction mechanism. It really show that our machine learning model that we produce here is very stable and can describe. And also the reaction mechanism that we get here is also described similar to the literature that we found before. This is for the discussion, just to summary and what we see from what we get from our own machine learning potential with the method dynamics to really looking at the full reaction mechanism. And we only pick the numbers that reported with experimental measurement that we pick from the papers. But overall, our simulation really give inside reaction mechanism and also give the number is close to the experimentals reported there. So with that, I hope that making use of machine learning models can help to at least accelerate computational, in this case, catalyst understanding, and hopefully will be discoveries because we have already efficient models. And of course, we always need to compare or find more accurate methods, either DFT or either more higher accuracy or experimental to confirm our predictions. And I believe that data efficient is really important. And hopefully that sharing data, it will also support our communities. And I would like to thank my team who did the work. This is Bun Palit, and also other team member also continue doing, and hopefully I can share their result with you. Yeah, with that, I'd like to thank for your kind attention. Thank you very much.
Thank you. Thank you, Nong, for the wonderful talk. So now we have time for Q&A. So if you have questions, you can feel free to drop it into the Q&A box. We already have a few in the Q&A session. So Nong, let me read the question for you to make sure everyone can hear it. So first question is from Yugi. What are your catalyst descriptors for predicting transition state activation energies?
So you mean the part 1, right?
I think so, yeah.
Yeah. The descriptor to looking at that, we use the absorption energy and reaction energy to describe the activation energy. Should I go back to the slide? Maybe I can show right? So I believe that this is the part that the questions. So we use the descriptor that we use for this case, we use binding energy, reaction energy to estimate. Yeah, we compare also with other simple methods, the BEP method, which is just only the initial and final, like a reactant and a product, and then we estimate. But with that method, it's not as accurate as our, let's say, GPR machine learning models, because we really have less point. Yeah.
So next question from marketers. So in your DFT simulation, do you generate a material that is representative of the lab materials, or you use simple slab models? So how difficult is DFT if you want to use representative materials from the labs?
So as you know that from the DFT, right? We cannot do the DFT larger than 1,000 atoms. We use the even not really large, but we have very diverse structures. Yeah, if I go back to my table, yeah, my apologies. Maybe I have to go to the table that I have. Yeah, actually, even this is some simple example that we're looking at. I mean, sorry, the way that we do, we really looking at yeah, my apology. I would like to go to this table that I have. Yeah, even I show such a simple like this, we rearrange. We have the phase diagram also from the previous work PCC paper, that we have varieties of the structure. Even this is small from the FT, but we have different phases, different rearrange, and different concentrations of, we have water, maybe 2 molecule, 4 molecule, 1 monolayer of water, until we increase it to bulk water. So they have really very different local environment to describe in the database. So this is the example that we have in the system. We looking at this is for the for fine tuning, right? We have the catalyst with some small, like a 2 by 2 by 2, and also some like a very small number of water, and also larger. So really looking at, so, and also larger. This is how but we cannot do larger than this to fine tune. We also cannot do very small, because otherwise it cannot capture realistics, because the interaction. Is that answer your questions? Yeah, the
I
intermediate.
think it also means the first one, right? The structure you modeled is, I think, is very representative from the usually surface science structures from the lab. I think that's why I also think why the small data sets can actually very useful for predicting new things. I think it really depends, right? Which system we can model.
Yeah, but then for the couple goal, right? You remember, because I only showed 2 cases. So we also have a variety of structure. We have bulk, couple goal, and different concentrations, like sometimes 50% or 25%, 75%, and so on. And also the surface, we also have like a surface of couple goal, like a 111, 100, and mixed surface, and also including also the water. So all kind of like diversities include in the training set, until we get the very stable machine learning model to do application. It was really large data, like I showed before. But at that time, there was no universal machine learning potential. We start from scratch, from zero. But now you see, we have a universal machine learning model. It's so nice that we can do fine tune, and then we can get less data point. But still, I don't know if what does it mean 16K is it's small or large. But for me, based on my own experience, I used to develop millions of DFT data point, different configuration. But 16K for me is small and can capture the full reaction mechanism. I think it's very robust and very I think it's hopeful.
Yeah, the next question, actually, you answered half of them already. So the second half is when you do the active learning, do you fine-tune the model from the previous iteration or you train from scratch, including the newly sampled data?
This is very good questions. We try both. First, we freeze the previous model and then we fine-tune only with the new data. And the second, we do from scratch again. So we compare the results and also we compare with the, let's say, the efficiencies of the cost of training. So what we did in this work, we trained from the scratch because it is basically you rearrange everything new. So then you can get also more reliable because it's also capture everything. So we test both. You remember the transfer learning method that we did? We freeze some part and then we also do fine tuning with only the new data point. This is also efficient and get really stable MD simulation with long-term MD simulation. But we didn't do complete reaction mechanism, but I'm not sure. But in this work, we try, Bunpalit try both. We freeze the models and then only do train the new data points. But sometimes because you have constraint, so we got a little bit like, we are not sure because we have to do this again and again. So the answer for the application, the result of this work, we do everything from scratch.
I see. So the next question, also the question I had actually, so in your hybrid AIMEDx GPR model, so you are fitting a GPR with high dimensional latent embedding from the machine learning potential to get uncertainty. Is this right? Is this right? Or how well does GPR actually handle that large dimension input?
Yeah, this is very good questions. So what we did is that we use the GPR to interpolate, right? To collect only in this. So let me repeat it. We use the GPR to generate the synthetic data. We collect the data, we collect information, which it is depending on the criteria that you would let them to put to your close or far from the target that you would like to go. But the good thing is that we collect only the structure, new structures, and also new energy that you have from the GPR and include in the training set, but you don't need to do DFT calculation from the hybrid functional. Do you understand?
Okay, I see. So in your training, you still train the neural network model.
Yes.
But use GPR, that's for sampling, better sampling with uncertainty.
That's correct.
I see. Yeah.
Then
Thank you.
It's super efficient.
So another question for the DFT database, is the data mainly for the methanol? I think maybe it means the ethanol reaction you described, or it could be used for many other reactions, such as methanation.
This I'm not very confident, but the model that we have, the workflow, it can work on any other reactions. Because the data that I trained, like NEB calculation, initial and final, this is only consider the ethanol reform, that the 14 reactions that I put it there. So I think it's okay, sorry. So I think what I show is it here, right? You can see that clearly that it might work some part, but we can borrow some, right? But we need to still include to the reaction that you have. So I think this is the workflow is there, the NEB tools, and to get, but you have to have the model that contain some of the intermediates that you need to have.
So another question, I guess this one is a little bit difficult to answer, I guess. So I'm new to DFT and relaxing a catalytic material about 300 items. It takes weeks to relax that material. Is there something I'm doing wrong?
Maybe you can help to answer, so Professor Shin.
Yeah, I'm not sure. It really depends on the material. Some material, even for the hundreds, even the tens of items, it's difficult to convert for sure. But for metallic system, usually it's much quicker, easier to convert. So it depends on materials.
Based on our experience, metallic is quite nicely. So we get even metal GGA or GGA, it's quite okay. But oxide with different oxidation state, like iron or cobalt or nickel, it's difficult. It's very difficult.
Mm-hmm.
We include the spins. We include more complex. It's difficult.
Yeah,
So we have
sure.
to select the right choice. What we do two-step approach. We start with the R2 scans plus van der Waals corrections to get the geometries, to get the structure so that we can get energy and the structure accurately. And if we would like to look at more accurate, we use the single point calculations to looking at like a more like a DOS or PDOS or spectroscopy. We use HHE06, but only single point calculation. So then we might have two database, and sometimes we can also use transfer learning or delta learning. Yeah, depending on the properties you would like to get it from your database. Yeah, our group now we start to use a meta GGA, R2 scans to construct machine learning potentials because we believe that it improves the properties. And if we want to look at more complex to understand the catalytic activities, we use hybrid functional to look at the oxidation state that can describe, like, especially with transition metals.
Yeah. So next question, I guess you didn't get a chance to go in details about electrochemical interface models. So what's your perspective on developing the machine learning potentials for reactions at the electrochemical interface influenced by the electropotentials?
This is very good questions. Actually, in our work that I show it here, we also don't have that part, right? Yeah, so let's go to this together. So right, we need to implement another workflow. Once we get this already, right? We need to put another workflow to add from what we have. Because of when we get such a over potentials, you need to add many others information there. Yeah.
So maybe one last question. Would it be possible to couple your machine learning potential metadynamics data with high throughput synthesis or operando spectroscopy datasets so we can iteratively refine both sides?
I think that would be really nice. I believe that yes. Yeah. I think we can do that.
Right.
Yeah. Because we have when we start to do a collective variable, like you can see here, right? It can directly, you can take snapshot, right? You can take snapshot and take the, and then we can do on the fly that you can really looking at the spectroscopies, like oxidation state, the XPS, XAS, or NMR to looking at it. The answer is yes. Yeah, because we can identify like a bond, the distance that you can really start to collect, and then you can extract that frames, each frames to looking at. This can be operandos. Yeah.
Great.
Yeah.
Fantastic.